Cool. All right, so I'll just get started.
Great.
The slides are more or less the same that I showed earlier, but I think there's some valuable data from across different types of ion channels. Just a brief snapshot of what we've been doing. There's some screening data which I can't show just yet, and also there will be a poster at Vancouver Ion Channel Retreat together with gene data about some recent stuff that we've done, specifically related to analysis. But I'll show data, and I think Ali's going to mention a few things in detail about the protocols and different opportunities later on. So the primary target that we initially looked at the IonFlux for was GABA-A, and the reasons were that we wanted something where we'd be able to run ligand-gated channels with a very good control over the liquid applications, and that's what we really like about the IonFlux. We're able to set up pretty complex liquid application protocols, and the responses are very quick. The fact that you can apply multiple different liquids to the same cells allows you to control your responses or normalize your responses to multiple different controls. So in the experiments that I'll show you next, we've applied reference GABA multiple times. We've then applied diazepam as a positive control for allosteric modulators. Then we've added a test PAM. We've then washed that out, reapplied diazepam to check what sort of enhancement we get. And then finally we applied 100 micromolar GABA in order to check where we are on the GABA EC50 curve. So what do I mean by setting up complex application protocols? In the screen here you can see, let me just put my pointer on constantly. What we're applying here from the 8 different application wells, first of all, reference GABA, then we're applying, in channel 7 we've got the vehicle control with DMSO, then we've got reference GABA, and then we've got applications from different compound channels for different allosteric modulators, and then we've got the 100 micromolar GABA applied towards the end of the experiment. And in this magnified view of the application protocol, the point that I want to make is that you can overlap and overlay liquid applications. So what's happening here is that from channel 7 I'm applying the vehicle, and from channel 6 I'm applying a compound, and the 2 liquid applications overlap, so that when the vehicle application finishes, you get a pretty much instantaneous liquid exchange. So that's done for both the concentration of compound here as well as down here. And hopefully what you can see is the end result is instantaneous changes and very fast responses. So this is for GABA-A using an in-house cell line with alpha-2 subunit. We're applying an EC20 of GABA and then different positive allosteric modulators in an open channel assay format. And what that means is that we first of all apply GABA to open the channels, and then we apply different compounds or DMSO, and then measure the enhancement of the current by these positive allosteric modulators. So what I hope you can see is that we can get very stable responses with GABA, and then very fast responses to different positive allosteric modulators. The graph on the left is just a single concentration of the positive allosteric modulators. The graph on the right shows a concentration response to the positive allosteric modulators. So you can see in green we have diazepam with increasing concentrations being applied and overlapped, and then we can measure the enhancement at different time points here. The way we like to analyze IonFlux data is using the gene data screener or nowadays analyzer application. The reason being that it's possible to analyze multiple plates of data at once, and it's also a pretty quick method. You can set up your own calculation cursors, multiple at the same time. And what I'm showing here is the experiment that I described earlier. So we have multiple reference GABA applications. Then we have diazepam applied here. We're washing that out, and then we're applying diazepam again in a concentration response, and then washing that out back to baseline, and then finally applying 100 micromolar GABA to check where we are in the EC50 curve. So you can see that you can set up pretty complicated experiments, get a lot of data out of your experiments, and you're able to normalize responses to internal controls. I've just highlighted here the kinds of calculation cursors that we can set up. So here we're measuring the level of current from baseline, and then the same thing in the concentration response. We're measuring the level of current in this particular zone, this concentration, versus baseline. And then all of these are normalized back against the level of current from the GABA. Okay, so what does that look like when you plot the data? On the left-hand side, I've shown the data that is generated from the single concentration protocol. So we're looking at DMSO, diazepam, LA38, and a couple of other known positive allosteric modulators. These responses have been normalized to the first diazepam response within the same cell, and therefore, because we're getting some desensitization and an imperfect washout, perhaps, in case of some compounds, diazepam comes down to about 80% of the initial diazepam response. But this is something that's pretty typical and would happen on manual patch as well. And on the right-hand side, I then have EC50s plotted for the positive allosteric modulators from the experiments that I showed earlier. And we're getting EC50 values which are in pretty good agreement with published data. And all of these experiments can be run very quickly. That's the other benefit of the system. The application protocol that I just showed you is a complete experiment, and you can test 32 compounds in an IonFlux HT plate in a protocol which lasts a number of minutes. So it's very, very quick. Another ligand-gated target, and this was something that we ran as a bit of a demo for someone where we'd never used these cells before. Essentially, we received them. They're a millipore, ready-to-assay cell line, HEC, nicotinic acetylcholine receptor alpha 1. Essentially just thawed the cells in an external buffer, put them straight into the IonFlux plates, and applied a few different agonists and ligands. So I wanted to show you here the speed of the response for nicotinic alpha 1. It's pretty rapid. If you look at the time scale on the bottom, this is in milliseconds, so we're getting very fast responses. And this is the protocol, again, has been set up to overlap the liquids, so you get instantaneous liquid exchange. This is the current versus time plot from that experiment, just showing what the currents look like with increasing concentrations of agonists. And essentially that's then been, we've taken the current values from the peaks and plotted those as EC50s for either acetylcholine or epipatidine, which is another known agonist. And basically the EC50 values that we've got from this one experiment, never run before with these cells or compounds, and we get values which are in fairly good agreement with published values again. And I guess the message here is the ease of use of the instrument. You can take a cell line that you haven't used before, set up an application protocol, put the cells on, and you should get pretty good data straight off the bat. Voltage-gated targets, so we've been using the millipore, I should say Eurofins here, obviously. Old habits die hard. And we've been using the Eurofins Tech human nav 1.8 plus beta 1 cells, and been running those. So on the right-hand side, I'm just showing some example current sweeps from an IV experiment. And then on the right-hand side, showing the derived values in a plot. What I would like to point out in the right-hand graph is that because we're using the ensemble plates here, measuring currents from up to 20 cells, for a cell line which doesn't routinely express a large number of the channels, we're able to get very good combined current amplitudes, and therefore a good assay window. And we're actually running some screening right now on the IonFlux for voltage-gated targets as well. And just to show you the comparison, here's the data from the Eurofins or millipore brochure for this cell line, and our IV is in fairly good agreement with the published values. There's a little bit of a shift in the peak and the reversal, but the buffer solutions were ever so slightly different, and we didn't have any compensation switched on here. So I'm quite happy with that. Same sort of experiment this time, steady state inactivation. Again, our VHAT value is in good agreement with the value from the Eurofins brochure. Slope is similar as well, so I'm pretty happy with that. And again, what you're able to do on the IonFlux, thanks to the liquid application, is you can put on different concentrations of the same compound, or potentially different compounds in a more screening-like mode, with wash-offs in between. So that's what I'm showing here. So from channel 8 in this case, I'm applying the vehicle controller DMSO, and from channel 7 to 1, I'm applying increasing concentrations of the test compound. So this is a 7-point concentration response experiment. And again, we're overlapping the liquid applications so that we get instantaneous change of the liquid. And in our case, this change takes place in between the measured sweeps. Therefore, the first sweep of your compound application should already show the block beginning. You don't have to do it this way, but we found it to be quite useful in order to speed up experiments a little bit. Here's an IT plot of that same experiment. So you can see in brown, we've got our DMSO control showing you that the currents are pretty stable over a long period of time. So the time scale here is in seconds, so you can see that our total experiment time here is about 40 to 45 minutes. So the cells last really quite nicely on the IonFlux instrument. What I'm also showing is compound responses to those increasing concentrations. And one thing that I do want to point out is that, because of the biology and partly the compound physicochemical properties, some of these don't necessarily wash out completely. In this particular experiment, we've used a fully inactivating protocol throughout the whole experiment. So I can highlight 2 points here. So if you're comparing, for instance, the blue trace, which is a standard local anesthetic reference compound, you can see that after the compound blocks some of the current, once you wash it out, it comes back to baseline very nicely. However, if you look at the compound in purple, you can see that upon wash-off, it comes off very slowly. And when we then plot the IC50s for these compounds, I'm highlighting a few compounds here which don't come off completely. There's the Abbott reference compound, and then a couple of our own. where the washout is incomplete, and therefore the percent inhibition per concentration is misleading. It's underestimated because the baseline that we're calculating from isn't quite right. Now there is a way that with the latest version that I think Ali is going to talk about, latest software version, you can stack your voltage protocols, so you could introduce perhaps a resting state voltage protocol for the wash-off, and then go back to your inactivated state for compound application. So it's something that's on the list of things to do. But I think overall, and I hope you agree, the data quality is pretty good. So I'm showing here averages and standard deviation from 4 experiments. And then correlating to the patch express, it's the same compounds as above, and I hope you can agree with me that the correlation overall is pretty good. The potency of some of the compounds which don't completely wash out, for instance, the ABAP compound, they are somewhat off the line. And also the other aspect is that the experiment here on the patch express was using the steady state detection for compounds, so the compounds were applied for a longer period of time, whereas we have a fixed limit to the time that each concentration is applied, and therefore we might underestimate the potency. But I would say the correlation overall is pretty good. And just as a sort of final point before handing over, how have we incorporated the IonFlux into our operation? The background, we've got a multitude of different automated EFIS systems in the lab, and we're responsible for generating both the lead optimization, but also increasingly up to HDS scale data. So how do you then minimize time and maximize throughput? For example, we're able to, thanks to the SBS standard plate layout for the IonFlux, we're able to dispense compounds directly from a DMSO stock plate into the IonFlux plate consumable on, for example, the Mosquito, and then simply dilute the plates with external buffer afterwards. Or alternatively, you can even fill the IonFlux HD plates with about 10 microliters of buffer, put those into the acoustic echo dispenser, and get your DMSO stock compound dispensed directly into the IonFlux plate that way. And again, dilute with ECS just before the assay, and you're good to go. So all of this has enabled us to really increase the throughput and make life easier for screening on the IonFlux. So in summary, we found the IonFlux to be very precise. It has very fast liquid exchanges, and you get very quick responses from your ion channels. The complex liquid application protocols enable you to really normalize your data very well to internal controls, which is much more EFIS-like than perhaps traditional HDS platforms might allow. We've been running both ligand-gated and voltage-gated channels. I think in our view the ligand-gated assays are very, very good. And because of the standard plate format, it's very easy to integrate into screening processes. So with that, I will finish, and I will try and